Alrighty, this is video number 24. It is the last video in chapter 5. This is chapter 5, section 5. And this is all about solving exponential and log equations. And it also utilizes the change of base formula. So there's kind of a couple different ideas in this section, but the first one's going to utilize this change of base. So I mentioned back in, I think, chapter 5, section 3, that if you use the LOG button on your calculator, that implies a base of 10. So if you have something like log, I don't know, 5 to the 25, you cannot put this in a calculator because it's not a base 10. So there's this change of base formula that will allow you to use your calculator if you don't have a base of 10. Change of base formula allows calculator use when the base is not 10. And so here's what that change of base formula looks like. If you have log a to the x, you can then use log of x over log of a, and I looked in a textbook actually, and they actually put these little b's in here, but then say the b can be anything as long as it's the same. So if b is 10, then you don't even need them there, right? If the b, and it would look like this, excuse me, if the b was 10, then you just have a log because base 10 is implied. If you were to put an e in there, log e of x, well, that gives you natural log of x over the natural log of a. And so you can use this if you have a base of e as well. So it's useful if you have any of those kinds of things. And here's how you would use it. If you saw a problem that said find log base 5 of 9 equals x, well, you could write that as 5 to the x equals 9, but what power of 5 equals 9? None. So this is not going to work, and you can utilize your change of base, where you just take log of 9 over the log of 5 and put this into your calculator. Be sure that you use the right amount of parentheses when you do that. And if you put that into your calculator, you end up with 1.3652, and that equals x. All right, super straightforward. Just plug right into your calculator. Do I have another one? I don't have another one. They're so easy. I didn't figure I needed to use more than one. So the other thing that we're going to do here is solving exponential equations. And you're going to do that using logs. So essentially they're inverses of each other, okay? And I think this will come up later. I do have a couple of steps here to do this. So if you see solve 3 times 2 to the x equals 42. Well, the first thing that you want to do is isolate the base and the exponent. get them all by themselves on one side of the equation. And we have a coefficient of 3 on here. So I'm going to divide both sides by 3 to make that happen. That leaves me 2 to the x. Whoopsie. 2 to the x. And 42 divided by 3 is 14. And now what you're going to do to actually solve this thing, because there's no log in there, right? And 2 to no power is 14. Well, it's a decimal power, but no power that we know. So what you're going to do is you're going to take the log of both sides and make the base of the log equal to the base of the exponent. I'm sorry, yeah, the base of the exponent. All right, so the base of our exponent here is 2. So I'm going to go log base 2 of 2 to the x equals log base 2 of 14. Well, you know from previous stuff that when you have a log and a base with a y, that just equals y, that this whole section cancels out. Right? Recall that from a few lessons ago. So this whole piece right here cancels out and leaves me x equals log base 2 of 14. Well, now you can use the change of base formula. So 3, use the change of base formula. To solve. So I'm going to have x equals the log of 14 over the log of 2. And when I plug that into a calculator, I get x is approximately equal to 3.81. Okay? That's how you're going to handle that. Let's do a couple more examples, and then we will be done with chapter 5. All right, so let's solve 12 to the 3x minus 2 equals 5. All right, so again, we want to isolate the base and the exponent. Well, that's already isolated here. There is no coefficient on the 12. So I'm going to take log base 12 of 12 to the 3x minus 2, set that equal to log base 12 of 5. Okay, well here, this is all going to cancel, leaving me just the exponent equals log 5 over log 12. So evaluate this as a decimal. And I guess I moved the 2 first and then added it to it. So let me evaluate that as a decimal. Log of 5 divided by log of 12. And I get 3x minus 2 equals 0.647685462. And then you're going to add a 2 to both sides. So you get 3x equals 2.6477. I'm just going to round here based on my 4th decimal place. And then divide by 3, and x equals 0.8827. All right. All right, here's the last one that we're going to do. If your bases are not the same, there's sometimes you have to do a couple of things here. So this next one is going to involve exponents on both your bases. Sorry, I was looking at notes there and just kind of blanked out for a second. All right, so here's what the problem looks like. Solve and then we'll see what the issue is. 81 to the x is equal to 9 to the 3x plus 5. Well, I have two different bases here, right? So this is the problem. So I can't raise this to a log of 81 because the right-hand side won't be correct. I can't raise this to a log of 9 because the left-hand side won't be correct. So when this happens, your job is to rewrite the bases as exponents that have the same base. Quiet, Dixie. Shh. So I live in the middle of the woods, right? Dix, it's okay, honey. And I have an outdoor cat, and she has cat food right outside my house. It's literally 8:30 in the morning, and there was a raccoon eating my cat food, and my windows are super low. So I think the coon is leaving, and the dogs are wigging out. Is what is happening. And that was my little dog, by the way. I have 2 pit bulls and this little dog. The 2 pit bulls are quiet and the little dog noisy. Anyway, when this happens, you need to rewrite the current bases as exponents with the same base. Dixie. Oh, base. This is base. And here's what I mean. If you see 16 and 32, these are both powers of 2. Right? 16, this is 2 to the 4th power. I don't even know. I think 32 is 2 to the 5th. That's got to be. Okay, and this is 2 to the 5th. So if I can write these numbers as exponents with the same base, now when I take the log, it's going to cancel both those bases out, right? So what can we do with an 81 and a 9? Well, you have a couple different options. 81 is actually 9 squared, right? So I could go, the 81 turns into 9 squared and raise that to the x power. And then this stays 9 raised to the 3x plus 5. And now what you would do is essentially, if your bases are the same, you can just drop them, because here's what you would do that you don't really need to see. This would become log base 9 of 2x equals, oh, I'm sorry, boo-boo, boo-boo, oh, super boo-boo. Oh, good Lord. Okay. Log, I take the base, and then 9 to the 2x equals log base 9 of 9 to the 3x plus 5. And so you end up with 2x equals 3x plus 5, because all the log base 9 of 9 cancel each other out. So when your bases are the same here, you can just get rid of them and turn this into an equation. You can skip this whole step. You don't need to do that, okay? So we can just go, these 9s essentially are gone, and these become the equation. 2x equals 3x plus 5, and then I solve. I'll bring this guy over here, so minus 3x, cancel here. Negative x equals 5, so x equals negative 5. All right. I want to do this another way. I didn't do it that way in my notes, actually. If I had the original problem, 81 to the x equals 9 to the 3x plus 5, I actually went base 3 with these. And here's why. 81 is 3 to the 4th power, and 9 is 3 to the 2nd power. And what's handy here is to know what to do with these multipliers, I guess. So we can leave off the base 3s, and I get 4 times x, so 4x equals 2 times 3x plus 5. And then watch what happens if we solve this. Now remember, x was negative 5 from this guy when we used base 9. So 4x equals 6x plus 10. Move that over, so I get negative 2x equals 10, and x equals negative 5. So it doesn't matter which way you do these. You can use any base as long as it's valid. I didn't even think about using the 9 until I was doing it here and didn't do it the way I did it in my notes. Okay, these are also not always going to be whole numbers. So another one that looks like this. Solve 8 to the 2x minus 5 equals 32 to the 3x plus 2. Now, yes, 8 times 4 is 32, but you need to write these as powers of something. So the 8 times 4 being 32 doesn't matter. You need to go to a base of 2 here, because 2 to the third is 8, and 2 to the fifth is 32. So you need to get your bases the same. So I'll rewrite these guys. So the 8 is 2 cubed, and the 32 is 2 to the fifth. Now I have my bases the same, so I can take the powers, 3 times 2x minus 5, get rid of these guys, right? That's what's happening, is equal to 5 times 3x plus 2. And now it becomes a simple linear equation that you're solving. So I have 6x minus 15 equals 15x plus 6. And let's subtract off a 6x, subtract off a 6. These go away, these go away. So this gives me what? 9x is equal to a negative 21. Did I do something goofy? I did something goofy either in my notes or here. Oh, yeah, I did. Look at what I did. Did you see it? Did you see it? Did you guys catch it? 5 times 2 is not 6, right? This is 10. Subtract off 10, subtract off 10. So that gives me a negative 25, not whatever I was about to get. And then divide by 9, divide by 9. So you get x equals negative 25 over 9. And just leave that in that form. Okay? All right, so that is the end of chapter 5. We'll do a chapter review and then a chapter test. Toodaloo for now.